Hello class, today we're going to look at section 12.1. We'll be doing operations with radicals. So we have 3 learning targets today. We want to identify or estimate square roots. Second, we'll define and we'll write square roots in simplest radical form, probably the most important thing of the section. And last, we'll perform mathematical operations with radicals, and after we do that, we need to make sure we write in that simplest radical form. 2 vocab today, we have principal square root and simplest radical form. So that principal square root, before when we took the square root of a number, we were always careful to put that plus or minus sign in front of it, right? Now we're going to kind of define the 2 different ones. So if we take just the square root of a, if we just have just radical in front of the number we're taking the square root of, that is the principal, or another way of thinking it, the positive square root, all right? And if we have a negative sign, so negative square root of a, that will be the negative square root. So you might hear me say the principal square root and the negative square root. Just know that it means basically the positive square root or the negative square root. So, a couple examples to get started. So if we look at this, again, before when we did this problem, if we looked at the square root of 25, we would say, all right, square root of 25 is positive or negative 5. But now that we've defined principal and negative square root, since we just have that square root sign in front of it, we're just going to say that this is equal to 5. All right. On the other side of that, in example B, we have the negative square root of 144, which we will say is negative 12. Okay. So if we have a negative in front of our square root, call it a negative. If we don't, just leave it as the principal square root or the positive. Now, when we run into something like this, a square root of 7. This is when we are going to use those perfect squares that we talked about earlier in the year. If you remember, the perfect squares are the numbers whose square root is an integer, all right? So square root of 1, square root of 4, square root of 9, 16, 25, 36, 49, 64, 81, 100, so on and so forth. Those are our perfect squares. You'll notice that 7 is not a perfect square. But here's what we're going to do. When we're estimating the square root of 7, we are going to find the 2 perfect squares nearest it. So the perfect square right below 7 and the perfect square right above. The nearest perfect square that is less than 7 would be 4. The nearest perfect square that would be greater than 7 would be 9. So here's the thing. The square root of 4 is 2. The square root of 9 is 3. So therefore, the square root of 7 is somewhere in between 2 and 3. Now, it's a little bit closer to 9 than it is to 4, so I'm going to say it's about 2.6 or so. Let's see what our calculator gives us. Now, there are ways to get closer. All right, we can start, estimating and multiplying them together. But just to give a general estimation, we're going to call this good for now. So we ended up getting 2.64, so we were pretty close. So that's how we estimate a square root. And last, that example D, if they do list a positive or negative square root of 9, you do have to say that that is positive or negative 3. All right? So keep in mind, principal square root, negative square root. If they give both positive or negative, make sure to give both. And to estimate, look at the perfect squares nearest to whatever number you are estimating. Let's keep going. Now, simplifying radicals and radical expressions. Before we start writing in simplest radical form, we need to learn how to be able to add these. And it's just, we're using the distributive property. Let me show you how. So example A over here. 5 root 6 minus 2 root 6. We can rewrite this as 5 minus 2 times the square root of 6. Because if I were to redistribute that square root of 6, square root of 6 times 5 is 5 root 6. Square root of 6 times negative 2 is negative 2 root 6. So really we can just subtract these, giving us 3 root 6. All right? Another way of thinking about it is they're kind of like terms. All right? It's probably not the exact vocabulary we want to use there, but it gives the idea of what's going on. For example, B here, we have 5 plus 6 root 7 minus 2 root 7 minus 3. All right? Again, I want you to be thinking like terms. So we have a 5 and negative 3 that we can add to give us 2. And then we have 6 root 7 minus 2 root 7, which gives us 4 root 7. And that's how we can simplify these expressions to make them look a little better for us. Just to make them look a little better for us. Example C is similar. So we have 8 root 3 plus 6 root 2 minus root 3, which you can just consider that 1 root 3 plus 2 root 2. All right, so I'm just going to gather my ones that look the same. So 8 root 3 minus 1 root 3 would be 7 root 3. And 6 root 2 plus 2 root 2 would be 8 root 2. And that's as far as I can simplify that one. And last, D. When we throw variables, it's still the same idea. So a root x plus b root x. We can rewrite that as a plus b root x. Now make sure to put the parentheses around this, because if you were to write this as simply a plus b root x, this could be written as just it could be read as a and then b root x as a separate term. So we have to make sure to put our parentheses around it. Great, let's keep moving. Now, writing in simplest radical form, all right? Writing in simplest radical form. To do this, we're going to be using the multiplication property of square roots. What the multiplication property of square roots tells me is the square root of AB is equal to the square root of A times the square root of B. All right, so for instance, I could say the square root of 8 is equal to the square root of 2 times the square root of 4. And I'm going to show you how that's very useful in just a second. But we can say a square root expression is in simplest radical form when all of the following conditions are met. First, no factor of the radicand is a perfect square other than 1. Second, the radicand contains no fractions. And last, no radical appears in the denominator of a fraction. I'm going to show you how to deal with all of those situations now. All right, so the square root of 12. If we want to write the square root of 12 in simplest radical form, what we need is we need to find the biggest perfect square that divides 12. All right? So if we look at our list of perfect squares, 1, 4, 9, 16, we want the ones less than 12, obviously, because we want a number that divides 12. And we want the biggest one that divides 12. Does 9 divide 12? No. Does 4 divide 12? Yes, it does. So here's what I can do. I can rewrite the square root of 12 as the square root of 4 times the square root of 3, because 4 times 3 is 12. Well, we all know that the square root of 4 is just 2. And then that square root of 3 will just leave a square root of 3. We rewrite this as 2 root 3. So we look for the biggest perfect square that divides 12, because we want to rewrite that perfect square as an integer. How about part B? Hopefully you know that the square root of 400 is just 20. But let's say you didn't notice that. So you're thinking to yourself, all right, what is a perfect square that divides 400? Well, I know that 100 divides 400, so I can rewrite the square root of 400 as the square root of 100 times the square root of 4. Well, the square root of 100 is 10, the square root of 4 is 2, 10 times 2 is 20. So it's just another way to get to the same answer. For C, the square root of x squared, it's very important to know that you can take the square root of any even-powered variable. Okay? The square root of x squared would be x. For some more examples, the square root of x to the 4th would be x squared. The square root of x to the 6th would be x to the 3rd. All right? So we can take the square root of any even-powered variable, and we just divide our power by 2. Which brings us to example D. the square root of a to the 5th times b to the 10th. Like I said, we can take the square root of any even-powered variable. But as you can see, a is raised to the 5th power. It's not an even power. Here's what we can do. Ready? I'm going to rewrite this as the square root of a to the 4th times a, because a to the 4th times a gives me a to the 5th, so I'm just rewriting that a to the 5th, times b to the 10th. Using that property I just learned, I can rewrite this as the square root of a to the 4th times the square root of a times the square root of b to the 10th. And as you can see here, I've rewritten it as much as I can as a square root of a variable to an even power. The square root of a to the 4th is a squared. The square root of b to the 10th is b to the 5th. The square root of a is just the square root of a. So we write our final answer like this, just in a little different order. A squared, b to the 5th, root a. And that's simplest radical form there. All right, let's look at some more operations. Let's look at some more. So, let's start with a up there. If we have something like this, 5 root 3 squared, what that really means is 5 root 3 times 5 root 3. And since everything is multiplication there, we have 5 times root 3 times 5 times root 3, I can just rewrite my order a little bit. So I'm going to do 5 times 5 times root 3 times root 3. 5 times 5 is 25. Square root of 3 times square root of 3 is square root of 9. Well, we know the square root of 9 is 3, giving us a final answer of 75. Example B, the square root of 3 times the square root of 6. I'm going to go ahead and multiply those together to give me the square root of 18. Now let's write that in simplest radical form. We need the biggest perfect square that divides 18. That's 9. I can rewrite this as the square root of 9 times the square root of 2, or 3 root 2. Now, when we run into something like C, we have the square root of 2 being multiplied by 6 plus root 12. We need to distribute that root 2 to both terms. So we will end up with root 2 times 6 is 6 root 2, plus root 2 times root 12 is root 24. I have a feeling I could rewrite that. So 6 root 2 plus, what's the biggest perfect square that divides 24? Well, 4 does. So I'm going to rewrite this as the square root of 4 times the square root of 6. Or 6 root 2 plus 2 times square root of 6. So we end up with 6 root 2 plus 2 root 6. And last, that example D. This is kind of a fun one here. 3 minus root 2 times 4 plus root 2. What you should see here is I have a binomial multiplied by a binomial. When we multiply two binomials together, we do the FOIL method. So let's FOIL. First, 3 times 4 is 12. Plus, outside, 3 times root 2 is 3 root 2. Plus, inside, negative root 2 times 4 is negative 4 root 2. Plus, last, negative root 2 times positive root 2 is negative root 4. Well, so that gives me 12 minus 1 root 2 plus, and the negative square root of 4 is negative 2. 12 and a negative 2 combines to 10 minus 1 root 2. So it's also possible we'll be foiling these as well. All right, we're almost done now. We're almost done now. Last couple. When we divide. Now, hopefully you remember earlier in the year, I don't remember. Oh, you know what? Properties of exponents. That's when I told you about this. When we take the square root of a fraction, we can rewrite it as the square root of the numerator over the square root of the denominator. So the square root of 16 over 25 can be written as square root of 16 over the square root of 25. Square root of 16 is 4, square root of 25 is 5. So simplified, that is 4/5. For B, similar situation. The square root of 7 over 16 can be rewritten as the square root of 7 over square root of 16. Now the square root of 7, we can't simplify that at all right? You could give the decimal, but we don't want to deal with decimals, especially when we're in a fraction, right? We want exact answers. So we leave it as the square root of 7. That's in simplest radical form. There's no perfect square that divides 7, so we just leave it square root of 7. Then the square root of 16 is 4. So root 7 over 4. For C, the square root of a squared, b to the third, over c squared can be rewritten as the square root of a squared, b to the third, over the square root of c squared. Now, I'm going to do this off to the side here. The square root of a squared, b to the third can be rewritten as the square root of a squared times the square root of b squared times the square root of b. Okay, notice I took my odd powered variable here, and I broke it up into square root of b squared times the square root of b, which allows me to rewrite this as the square root of a squared is a, square root of b squared is b, times the square root of b. So I end up with a, b, square root of b, over square root of c squared is c. And now for example D. The square root of 9/5. Now, here's the thing. Again, we rewrite it as the square root of 9 over the square root of 5, which can be rewritten as 3 over root 5. But here's the thing. We are not allowed to leave a radical in the denominator. Okay? Miss G calls that a fire in the basement. Where's the worst place to have a fire? In the basement, because heat rises, right? Heat and smoke rises. Fire in the basement. Here's how we deal with that. We are going to multiply this by a really clever form of the number 1. Take whatever your radical is in the denominator, and we're going to multiply the top and bottom of this fraction by that radical. Now, this blue number here is just 1. We're not changing the value of the fraction if we're multiplying by 1. Root 5 divided by root 5 is 1. We're not changing the value of the fraction, we're just changing how it looks. So we end up with this. 3 times root 5 is 3 root 5 over root 5 times root 5 is root 25, or 3 root 5 over 5. So to get rid of the radical in the denominator, multiply the top and bottom of the fraction by that radical. All right, this stuff takes practice. Make sure you're doing your homework, and I will answer any questions the next time we meet. That's 12-1. Thanks.